Hi everyone, and welcome to this tutorial on executors in HPX. Today we'll explore what executors are and how they let us control how tasks are executed. We'll look at the main executor types and walk through simple examples so you can see how to choose the right one for your application. For this tutorial, you need to have your HPX installation complete and know how to compile and run an HPX application. For this, we have a different tutorial with a Hello World example, which I will link here. What is an executor? An executor is an abstraction that decides how, when, and where a piece of work is executed. Instead of us having to manually create threads or manage a thread pool, we can hand our tasks to an executor, and it takes care of the details of running them. The nice thing about executors is that they separate the what from the how. As developers, we only need to describe what should run, for example, a function or a task. The executor then decides how it should run, whether that's synchronously on the same thread, asynchronously on a new thread, or in parallel across multiple cores. This makes our code much more flexible because we can change the execution strategy without rewriting our algorithms. HPX already provides a rich set of executors that follow this idea. We provide a unified API so you can switch between different execution strategies without rewriting your algorithms. HPX provides multiple executors, but let's focus on the three most important ones. The first executor I want to introduce is the parallel executor, which is also the default in HPX. Every time we schedule a task, the executor creates a brand new thread for it. This makes it simple to use, and it works quite well when our tasks are relatively large and not scheduled too frequently. However, the downside is that creating and destroying a thread every single time comes with some overhead. So if we're dealing with lots of tiny tasks, this overhead quickly adds up and can actually hurt performance. The next executor is the fork join executor. Instead of creating a new thread each time, this one spawns one thread per CPU core right at the moment the executor is created. These threads then stay alive and ready for use whenever we need them. The advantage of this approach is that we don't pay the cost of repeatedly creating and destroying threads. This makes the fork join executor particularly efficient when we have a lot of parallel work happening in sequence. On the other hand, if we don't actually have that much work to run in parallel, those threads remain active and occupy resources that could otherwise be used for something else. Finally, we have the sequential executor. As the name suggests, this one runs everything synchronously on the calling thread, so nothing is executed in parallel. Even though this sounds like a step backwards, it's actually very useful in a few situations. For example, it's great for debugging because the execution is deterministic. It's also handy in cases where parallelism doesn't really provide any benefit, or when we just want to keep the same executor-based API, but run everything sequentially. Let's look at a real-world example where executors make a big difference, the LULESH mini application. LULESH is a hydrodynamics benchmark used in high-performance computing, modeling how materials behave under extreme conditions. Its computation consists of many parallel loops that run one after another, update positions, compute stresses, calculate time constraints, and so on. We will see how LULESH runs with two different HPX executors. On the left, we have the default parallel executor. For each parallel loop, a new set of HPX threads is created and then destroyed once the loop finishes. Since LULESH has many sequential parallel loops, this means that we are constantly creating and tearing down threads. Even though HPX threads are lightweight, this repeated setup introduces measurable overhead. This approach works fine for large loops, but in LULESH, the loops are frequent and the overhead starts to dominate. On the right, we have the fork join executor. Here, the threads are created only once at the beginning and then reused across all the sequential parallel loops. In other words, instead of hiring and firing workers for every loop, we keep the same workers busy and just hand them the next task. This reuse is much more efficient for workloads like this one, reducing overhead and significantly improving performance. In practice, this made a huge difference. In the LULESH study, the fork-join executor achieved significant speedups, in some cases more than twice as fast as the traditional OpenMP implementation. So this figure really illustrates the main difference. The parallel executor gives flexibility but comes with overhead, while the fork-join executor is optimized for workloads with many back-to-back parallel regions. So choosing the right executor for the workload can have a big impact in practice. Now that we have explored the main executors in HPX and seen how they can be used in real-world examples, it's time to write our own custom executor. We're going to create an executor that can annotate tasks. Annotations are really handy for debugging and profiling because they let you see exactly which task is running when HPX schedules it. The idea is simple. An annotating executor wraps the task it runs and gives them a descriptive name. For this demo, we'll support two basic operations. Post, which schedules a task in a fire and forget style, and sync execute, which runs the task immediately and returns the result. The extra twist is that whenever a task runs through our executor, we'll tag it with a string. The task itself doesn't change, but now you have much better visibility for logging, debugging, or performance analysis. We start with the usual HPX headers, HPX main, executors, async, execution, and post. And then the important one, annotated function. That's the piece that lets us attach a human-readable label to any task. Now, let's define our executor. It's a template over any base executor. I'm calling it Simple Annotating Executor. It's just a wrapper around another executor. So it stores two things: base, the underlying executor we are wrapping, and annotation, a string literal that will be attached to every task. The constructor just takes an executor and the string, moves the executor into base, and then stores the annotation. Very simple. Let's write the post overload for our custom executor. This is a function that HPX will call whenever we use HPX parallel execution post with our executor. So we start with a function template. F is the type of the function or callable we want to run, and TS is a parameter pack for any arguments that will pass along to that function. Executors in HPX customize operations like post and sync execute through tag invoke overloads. The first parameter is HPX parallel execution post T. That's just a little tag object that tells HPX, hey, we're customizing the post operation here. So we don't need the value itself, but it has to be there so the overload is picked. The second parameter is our executor, simple annotating executor, const reference exec. This gives us access to the executor state, in our case the annotation string. And finally, f double reference f and ts double reference ts are the function and its arguments. Notice the double ampersands. This is forwarding references, so we can perfectly forward whatever the user passes in. Inside the function, what we're doing is very simple. We call HPX post, which schedules a task to run asynchronously. But before we give it the function f, we wrap it with HPX annotated function. That takes the original callable and attaches our annotation string exec.annotation. This way, when HPX runs a task, it knows what it's called. That shows up in tools like profilers, debuggers, or logs, so you can trace which task is which. Finally, we forward all the arguments with stood forward TS, making sure everything is passed along exactly as it came in. So overall, this overload says, whenever someone calls pause with our executor, take their function, wrap it with an annotation, and then post it just like normal. The only difference is now the task carries a name. Now let's do the same thing for sync execute. Remember, sync execute is the synchronous version of post. So instead of just scheduling a task, it runs the task immediately and gives you the result back. So again, we make it a function template. F is our callable type and TS are the argument types. Same as before, we want this to work for any function and any arguments. Here's the tag invoke overload. The first argument is HPX parallel execution sync execute T. That's the tag object HPX uses to look up a sync execute overload for this executor. Next is our executor, simple annotating executor, const reference exec. Same idea as before. We need it so we can grab the annotation string. And then we have the function and its argument all perfectly forwarded. Inside the function, instead of calling HPX post, this time we call HPX parallel execution sync execute. Notice that here we pass in exec.base, which is the underlying executor we are wrapping. So we are saying, hey base executor, please run this function synchronously. But again, before we pass in the function f, we wrap it with HPX annotated function and attach our annotation string. That way, even though the function runs immediately, HPX still knows its name for profiling and debugging. And finally, we forward all arguments with stood forward TS, just like before. The return value from sync execute is whatever the function f returns. That's why our overload itself returns auto. So just like with post, this overload adds annotation to the function. The difference is that now the function runs synchronously and we return the result right away. Let's make a simple function to run with our executor. This one is called compute square. It just takes an integer x, prints a message that it's running, and then returns x times x. So if we give it 7, it will return 49. Easy. And here is another example. Say hello. This one doesn't return anything. It just prints a message when it runs. We will use this one to test post, since post doesn't care about return values anyway. Now let's jump into main. First, we create an instance of our simple annotating executor. We give it a base executor. Here I'm using HPX execution parallel executor, and a string my custom task. That string is our annotation, so every task that goes through this executor will be tagged with that name. Next, let's try sync execute. We call HPX parallel execution sync execute, give it our executor, our function compute square, and the number 7. Because it's synchronous, this will block until the function finishes, and it will return the result. So here, compute square 7 returns 49, and we print that out. Then let's test post. We call HPX parallel execution post, again with our executor and the function say hello. Unlike sync execute, this doesn't give us a result back, so it just schedules the function to run in the background. When it runs, we'll see the message from inside say hello. I've already compiled the code, so let's go ahead and run it. We have two tasks here. One we run synchronously using sync execute, and another we post asynchronously with post. So both tasks are using the same annotation string, my custom task. Even though the annotations aren't printed by default, they are there internally. So the point of annotations isn't really to show up in your console output. They are meant for HPX internal tooling like debugging and profiling, so you can track tasks and see exactly what's running when. If we wanted, we could also create different executors with different annotation strings, so each task gets tagged separately, which makes it even easier to follow what's going on in bigger applications. Alright, so let's quickly recap what we've done. We created simple annotating executor, which wraps any executor and lets us tag tasks with a string annotation. Sync execute lets us run tasks synchronously and actually get a result back. And post is for asynchronous fire and forget tasks. So annotations help us debug and profile HPX tasks, especially when many tasks are running concurrently. And that's it. With this, we have a fully working annotating executor in HPX. Now that we have seen how to create a custom executor for post and sync execute, let's take it a step further. We'll see how to use a custom annotating executor with a parallel algorithm in HPX. This is useful because parallel algorithms in HPX, like for each, schedule many tasks internally using bulk async execute. By attaching an annotation to each task, we can track exactly what's happening in debuggers or profilers. As usual, we start with the necessary headers, and then we define a simple annotating executor that wraps a base executor and attaches a string annotation to each task. This is similar to the example before, so here's the code. We define execution category to inherit the capabilities of the base executor. So we do using execution category equal HPX traits executor execution category T of base executor. This ensures our custom executor behaves just like a normal parallel executor and is compatible with HPX algorithms. Now let's write the overload for bulk async execute. This is the function that HPX parallel algorithms, like for each, transform, or reduce, call internally when they schedule many tasks at once. So just like before, executors in HPX customize these operations through tag invoke overloads. So we start with a function template. F is a callable, the function or lambda we want to run. Shape is a collection that represents all the indices or elements we'll launch tasks for. And TS is a parameter pack for any additional arguments that get passed to each task. The first parameter, HPX parallel execution bulk async execute T, is the tag object that tells HPX we are customizing how bulk async execution works for this executor. The second parameter is our executor, simple annotating executor, const reference exec. This gives us access to the annotation string that we stored when the executor was created. And then we have the callable f double reference f, the shape, and any extra arguments ts double reference ts. Notice again the double ampersands. Those are forwarding references, so we can perfectly forward everything the user provides. Inside the function, we simply delegate the real work to the underlying executor exec.base. So we call HPX parallel execution bulk async execute, and then we give it exec.base, the annotated function. So HPX annotated function stood forward f exec.annotation, the shape, and then stood forward ts. So here's what happens step by step. We wrap the user's function f with HPX annotated function, adding our annotation string. Then we forward the shape and any additional arguments unchanged. The underlying executor base takes care of actually launching all the tasks asynchronously. So this means that for every element in the shape, HPX will create one asynchronous task that runs the annotated function. So the annotation string helps identify these tasks in profiling tools or logs without changing how they are executed. So overall, this overload says, whenever HPX wants to launch a batch of asynchronous tasks through our executor, take the function, tag it with our annotation, and forward it to the real executor underneath. That's all. Our executor stays lightweight, only adding labels to tasks, while the underlying HPX executor handles the scheduling and execution. At the end of our implementation, we need to tell HPX what kind of executor we have created. So that's done by specializing a few executor traits inside the HPX execution experimental namespace. These traits are how HPX recognizes what capabilities an executor has. For example, whether it can run tasks one way, fire and forget, two-way, returning a future, or never blocking. So let's unpack this. This trait specialization says, our simple annotating executor supports exactly the same kind of operations as its underlying executor. If the base supports two-way execution, then our annotating executor can too. So by inheriting from the base executor's traits, we don't have to manually redeclare anything. We simply forward all its capabilities. So this step is important because HPX parallel algorithms use these traits internally to check whether an executor can be used with a given execution policy. So overall, this section tells HPX, treat our simple annotating executor exactly like the executor it wraps. The only difference is that we add annotations. Now let's jump into main. First, we create an instance of our simple annotating executor. We need to give it a base executor for which we will use the parallel executor. So we are doing using base executor equal HPX execution parallel executor. Then we wrap this base executor in a custom annotating executor. So we do simple annotating executor, let's call it exec, and we give it the base executor and a string for each task. That string is our annotation, so every task launched through this executor will be tagged with that name. Next, we set up some data, just a simple vector of integers from 1 to 5. We will run a parallel algorithm over this data to show how our executor integrates with HPX algorithm framework. Then comes the interesting part. We call HPX for each with the parallel execution policy, so HPX execution par, and we attach our executor using .onExec. This tells HPX to use our custom annotated executor when scheduling the work. We iterate from data begin to data end, and inside the lambda, for each element x in the vector, we print the message showing which thread is processing it. And then we square the number. Because this is a parallel algorithm, HPX runs these iterations concurrently across multiple threads, and thanks to our executor, each task is annotated with a label for each task. This annotation doesn't show up in the console, but it's recorded internally for profiling and debugging. Finally, we print the results to confirm that all numbers were squared. So overall, this example shows how a custom executor can be seamlessly plugged into HPX parallel algorithms, letting you combine annotations, parallelism, and high-level algorithm interfaces, all in a clean and reusable way. I have already compiled the code, so let's run it. Each line shows which element of the vector is being processed and on which thread. Because we're using a parallel algorithm, different elements can run at the same time, and that's why the order of the processing lines isn't the same as the order of the data. HPX distributes the work across multiple threads to speed things up. After all tasks finish, we print the final results, the squared values of our original numbers, and that confirms that the algorithm ran correctly. Behind the scenes, every one of these tasks was tagged with an annotation string for each task. Even though we don't see the annotation in the console, it's recorded internally, and those annotations become really useful when profiling or debugging because they can help you see which annotated tasks were created, scheduled, and executed so you can easily trace performance or behavior in more complex programs. So in short, the program runs a parallel for each iteration is annotated, and HPX handles all the concurrency automatically. Thanks for sticking around. I hope this gave you a clear idea of how to use and extend HPX executors. Happy coding, everyone!